This week on QDL, we have a tech corner. We're going to look at the OmniScan X3 phased array flaw detector. This is an ultrasonic non-destructive inspection tool that you can use to inspect welds, pipelines, corrosion-resistant alloys, and a lot more. We'll learn more about that in 30 seconds when we come back. QDL. QDL is your weekly look at who and what is making news in the world of quality. I'm Dirk Ducharme, Editor-in-Chief of Quality Digest, and I'm joined today by Curtis Dickinson. He's a Senior Application Specialist with Olympus Corporation. Curtis, thanks for joining us today.
Dirk, happy to be here.
We are looking at the OmniScan X3. This is an ultrasonic inspection tool, right?
Yes, sir. This is our third generation in the OmniScan series, the OmniScan X3, which is a multi-purpose ultrasonic testing machine that's capable of ultrasonic testing, time-of-flight diffraction, phased array, and then the latest addition for the OmniScan series, which is FMC TFM inspection.
Okay, and this is an update. This is an update to an older model, right?
Yes, it is. The OmniScan series, early 2000s, we had the OmniScan MX. In the 2010s, we came out with the OmniScan MX2 and then the SX. So this is our latest in that OmniScan series.
Okay, well, take us through it.
Yeah, so what we're seeing here on the X3 is an updated design of the instrument itself and just the overall box. We tried to make some good improvements to that workup in durability, in access to different connections for the machine, and then improve the interface for the instrument, just the actual display itself. So we put a lot into the overall design of just the box itself. Some changes that were made to the OmniScan from a previous user's perspective. First and foremost, the X3 is a new change for us, and that comes in the back of the unit. The M in MX and MX2 stood for modular, which referred to the back portion of the unit. But that back portion of the unit is now fully integrated into what we would call the mainframe or the front of the unit, which makes it a little bit easier for us to meet IP certifications. This unit is an IP65 certified instrument. Okay. And then with that change, came some differences that we've made in how you connect and how you get around the unit. On the top side of the unit, we have our typical phased array connection. We have our encoder connector, which is pinned out for 3-axis worth of information. And we've added a second UT channel so that our users that take advantage of TOFT inspections don't have to necessarily steal from our phased array connector. Right. So there's 2 dedicated channels there. And then we've also added some better connectivity on the side of the instrument as well. HDMI output, USB 3.0, 2 batteries that are hot swappable. And then the big change for connectivity on the unit is adding Wi-Fi in for the system. Okay. So there's a slot on the side of the unit that's there for a Wi-Fi dongle that will give the technician access to Wi-Fi in the unit that you can use for file transfer, for software updates to the unit, and some other cloud-based functionality that we've added to our Olympus portfolio. Okay.
And also I know it's a hard Ethernet connection there
yes.
as well, right? Okay.
That's there for either direct data saving to a PC or eventually, hopefully, slaving the unit to a PC.
Okay, perfect. So take us through the operation.
Yes. So in addition to the just overall box design, we also try to make a lot of software improvements in addition to a lot of hardware improvements to the system. What you're seeing on the front here is a basic phased array setup for the instrument. So on the display here, we have a sectorial scan on the S-scan display alongside of the analog A-scan display. So this is a very traditional type of phased array inspection that you'd see on this type of unit. We're inspecting from 40 degrees to 70 degrees with the blue line running through the display here being our toggle for the A-scan display. Okay. But
so for those of us like myself who aren't totally familiar with, if we can go back to the screen capture here.
Yes.
So the left side here is I think that's the analog display. That's the output. That's what the sensor is seeing at that particular point along the blue line that runs through the center of that that white segment, right?
Correct. Okay. So we're firing one angle at a time from 40 to 70, and this toggle can be moved to look at or identify different indications that show up within this segment.
Okay, so the blue line is like a cursor, and as you lay that over, whatever's underneath that is what shows up on the left-hand display.
Correct.
Okay.
The display on the left, what we typically call our A scan or analog signal, is the electrical representation of the sound that went through the material and then came back to the transducer.
Okay.
So we see that in depth and then in strength of the signal or amplitude.
Okay. And then in the actual wedge-shaped, what do you call that area, though? The white wedge-shaped area.
It's called a sectorial scan.
Okay, there.
Yep.
So in the sectorial scan, I saw 3 little blips. Now, are those flaws then?
Could be. Depends on the inspection that you're performing. We have just a demonstration block here. And yes, we have 3 indications that show up on the display here, which are these 3 stacked holes on the end of this block there. And then if we go live with the system and we start scanning with the transducer, then typically the inspector would look for any indication that they may see, either scanning in and out on a part or perhaps scanning across a part. And then when they find a particular indication that they want to look for, or that they identify, they can skew the transducer, raster in and out on that indication, and perhaps stop when they've got a good view of it.
So you're basically rotating the sensor to maximize the signal?
Correct.
Okay.
Maximize the response,
okay,
so that we can pause the instrument and then further evaluate with both what we see on the sectorial display and on the A-scan.
And I think you just mentioned pause the instrument, so I think that's a key bit, right? I mean, you may not always be able to just to leave the sensor like you're doing right now in place. If you're measuring something vertically, you got to hold it.
Correct.
And then you need to freeze it, so then you can go and do your analysis, right?
Yeah, as inspectors, you're always in awkward situations with the part that you're inspecting in your equipment.
Okay.
You might be scanning something vertically or overhead, or you've got your arm wrapped around something strange. So yeah, you're always just trying to maximize an indication and then freeze it or pause it on the system so that you can properly analyze it.
And you can record, I'm assuming you can record these measurements as you're going?
Yes. Actually, one of the biggest benefits that we've adjusted for the X3 is the amount of data that you can collect. The system has a 64 gigabyte internal SSD with a max file size of 25 gigabytes.
Okay.
So that's a very large upgrade for the OmniScan platform, and it means the technician can collect, store, record large amounts of data without stopping.
Okay.
So I'm going to actually go back live here. One of the other improvements that we try to make with our systems is just the overall user experience with the system, whether that be setting up the machine, adjusting the settings for an inspection, or calibrating the system. So within the software, we've tried to make it easier for the technician to kind of go through that process, and that's where the scan plan menu comes into play.
Okay. So this would be like a setup.
Yeah, correct. Okay. So the technician here has access to all 3 phases of that setup portion, which is adjusting for the component that you're testing, material type, the thickness for the component, may even adding in what we call an overlay or an image of the internal makeup of the part so that we can better interpret the signals. And then an easy transition into the equipment that we're using, which probe and wedge you have selected, adding multiple different transducers on for a more complex inspection, and then in the last step, switching over to what you want emitted from that transducer, what type of inspection that you want to perform, whether that be standard sectorial scan, linear scan, compound scan, or switching into our new FMC TFM inspection.
Okay. And so then, you would store as many setups as you need for different types of inspections. Then all the technician has to do is come in, hit that particular setup routine, right? And it's ready to go, right?
Correct.
Okay.
Correct. So I can get through this entire process here for a single transducer with a single group, or work through this exact process with multiple transducers, multiple groups. Hit the done icon up here in the top right, and the system will compile all of that information all at once. So it makes that very handy if you're, again, running a more complex inspection with multiple pieces of equipment, different settings for different parts of the inspection. It's easy to set that up, and then in just a couple clicks there, you can set a name for that inspection and then save that as a setup file.
Okay.
To be recalled for later.
Ah, perfect. Okay.
Yep. And that setup can save both the parameters for the inspection and then also the calibrations for the inspection as well. So typically the operator would perform their setup, adjust all the parameters, and then come back through and perform one of the calibrations for the unit, which we've also tried to improve on a little bit and make it easier for the technician. Have all of the calibration options in one place, make them a little bit easier to work through in terms of how much information is on the display, on the screen, and then just really try to improve upon the overall performance of those calibrations. So if I just quickly run through one of those calibrations here, this is what we would call a sensitivity calibration, where instead of one particular position having a different amplitude reading across all of the angles, we want that amplitude reading to be the same across all those angles. So I can very, very quickly show the instrument an indication, collect the amplitude reading all the way across, and as I complete that out, the instrument will quickly adjust and compensate for that amplitude.
Oh, okay, okay.
So I'm sitting in a kind of funky position, but really the benefit of this system is just the speed with which that can be done. We can accept that calibration.
So they basically they have a calibration artifact that they use to calibrate against, right? So
correct.
Yeah, okay.
They would have a block similar to this, either with maybe a notch cut into the top or bottom of the block, maybe a side drill hole, or even on this block here, you have a radius on this left-hand side that you would use to adjust either for distance or maybe adjust for amplitude.
Okay, excellent.
Yep.
So this, what we've been looking at, this was kind of your traditional ultrasonic inspection, right? This display
Correct.
and so forth? Okay.
Yeah, this type of inspection that you're looking on the screen here is most common.
But better on the OmniScan X3 because it's been improved.
Very much so. One of the other additions that we tried to include outside of just the software improvements, so just the workflow that you go through for setup and calibration, we also try to make some hardware improvements to the system.
Okay.
And that correlates to the resolution of the signal that we have on the display. We've added what's called a 16-bit A-scan for this system. So we have a lot more data that can be used to represent the A-scan signal, which correlates to a higher resolution signal that really pops on the display. And then we've also tried to do things like improve the acquisition rate for the unit, improve the number of samples that are available on the system, and then increase what we call throughput for the data. So in terms of a generic phase array inspection, we've tried to improve it by having a higher resolution A-scan, a higher resolution image, and then allowing the technician to collect more data and do it faster.
Now, I've been calling the OmniScan X3 an ultrasonic tester. Is that the correct terminology?
That's very accurate.
Okay.
Every type of inspection that you can perform on the X3 is ultrasonics in some variation or some form.
Now you have another display that you want to show. It's kind of the next latest and greatest thing that you're doing with the OmniScan, right?
We do. We have a newer inspection technique that is coming up in industry called FMC TFM. It is an alternative way to use a phase array transducer in the way that the sound is sent and received, and then taking that data and generating an image. So what we see here on a standard phase array inspection is we see individual angles being sent from the transducer. So one angle travels down through the material, reflects back, and then we take that information, we put it on the display. I'm going to open up our setup file that we have made for the FMC TFM and kind of explain that a little bit.
And TFM means, again, what?
So there's two parts. So you have FMC, which stands for full matrix capture.
Okay.
And then you have TFM, which is total focusing method.
Got it. Okay.
The two parts work hand in hand. The FMC is the operation of the transducer.
Kind of the data collection part.
Yes, the data collection works like this. You take one element from the transducer and we send out a sound wave. When that sound wave reflects and comes back to the transducer, we actually receive that sound wave on all of the elements of the transducer. And what we do is we repeat that type of sending and reception across all of the elements of the transducer.
Okay.
So what we end up with is a massive amount of data.
Okay.
A lot of data.
Yeah.
For a 32-element transducer, that's over 1,000 A-scan signals. For a 64-element transducer, that's over 4,000.
Okay.
So we have a lot of data that we can work with. What the TFM does, the total focusing method, is it takes that data and it places it into our image. Okay. And the image, which you're seeing on the screen now, is essentially a giant grid. We have grid lines that go across the display. We have grid lines that go up and down the display. As many as 1,024, both across and down. Okay. So a very high resolution capability image. We tell the machine how to calculate the time of flight to each one of those grid points. One of the downsides of a standard phase array inspection is that when a technician finds an indication, so as I'm scanning it back and forth across the block there, I see our stack of 3 holes there. Okay. If I move a little bit further down the block, oops, stuck. There we go. I see there's a crack down at the bottom of this block there. Okay. I can see the bottom of it, and I can see little tip signals working their way up. In a standard phase array inspection, a technician may find an indication somewhere within their inspection and have to adjust settings to refocus the data to get a good image of that part. Okay. But because of how we calculate the time of flight to each of the grid points in the TFM display, we actually get a more in-focus image, a tighter resolution image at each one of those grid points without having to adjust any settings. Okay. So it optimizes the image of the indications that we see in a part without the technician really having to adjust too much in real time.
And I also noticed that looking at that display, it's also more intuitive what you're looking at. Like you have those 3 holes, they're stacked one above each other, just as they are on your test specimen right there.
Correct.
But with the segment display, they're kind of staggered just because they're being seen at an angle, right? Yes. I mean, so it's not as intuitive, at least to somebody like me, it's not as intuitive. Whereas I look at that other display and I can see exactly what's there. I can see 3 holes stacked one right above
the display itself is a little bit easier to understand because there's less information. It's just a box.
So like even a dummy can like me can actually figure out what's going on there. Hey, I see what that is.
I wouldn't go that far, but it's very easy for the technician to adjust that part of it. So the same way we adjust the part and the material type, the thickness, the picture of the component, the probes and the equipment, all that works exactly the same. But then when you get down to the setup part of the TFM, it is a little bit easier in that you're just adjusting where the image takes place. It's just a square that you're adjusting, or what we call the zone on here. Okay. There's a couple tools that we've added to the X3 when it comes to that type of inspection to make it easier on the technician to know where should the probe be sitting, where should that image be coming from, and what we call our AIM tool. So on the screen right now, what you're looking at is our acoustic influence model, which is essentially what we call a scan planning tool. So this model shows the technician the expected reflection based on the different measurement modes that you can select. Okay. So this will, again, help the technician figure out where should I put the probe, where should I tell the machine to show me my image. But then when it all boils down to it, after you make that adjustment, then what you're looking at is just the result of that image. Just, again, top of the screen is the top of that box, bottom of the screen is typically the bottom of the part, and then the technician can adjust either further out or closer in to whatever part of that inspection that they want to key in on.
So you mentioned this is something that's new to the industry, this technique. Why would somebody now use the older technique you showed us, the segment array? Is that what you called that?
Just traditional phase array, yes.
Okay. So why would you use that method in place of this newer method that you were just showing us? I mean, is there a trade-off there? Or?
Well, first and foremost, for some applications or some inspections, our codes and standards are still trying to catch up to the technology.
So they're used to the other. Okay.
Yes. So we have some ISO standards that are being worked on right now. The ASME code recently added FMC TFM to their standards, but a lot of other industries haven't really come up with criteria for how to use this technique for their inspections. So you have that case. And then in terms of just advantages and disadvantages of, say, standard phased array and FMC TFM, one is just the sheer amount of data that you're collecting. So that's a lot of data to process. On FMC TFM inspections, we're typically running at slower scan rates, scan speeds. So technicians are collecting data at a lower rate for most inspections as compared to what you'd get on traditional phased array. And then, but conversely, with FMC TFM, you get a better image. So in some cases, it actually can be beneficial to maybe do both.
A quick scan to find an area of interest,
Correct.
and then the other one to kind of focus in on a particular area.
Yes.
Okay.
Sure. It's nice to have both techniques in the same package so that you can run one for a quick inspection, and then if you want to take advantage of the better imaging that you can get with an FMC TFM inspection, then you have the flexibility to do that here.
Okay, great. And where is this being used mostly?
Our number one area for OmniScan usage right now is definitely weld inspection, whether that be for oil and gas or petrochemical. But weld inspection is definitely one area that we've always focused on and keyed in on. But that doesn't mean that the box can't be used for other industries or other applications.
Okay, that's great. Anything else you want to touch on here?
That's the majority of the system. We have some tools here on the FMC TFM side to kind of help technicians make sure that they're performing their inspection correctly, meeting certain resolution standards, certain amplitude fidelity for the system. But really the only other good key aspect of what we're doing here is continuing to kind of push the boundaries of what you can do with FMC TFM and adding some live processing on here. So we're taking advantage of what we call an envelope function on our display here to really show good images for the system. So this is a nice tool that a technician can toggle on, toggle off, and really show crisp, clean images for either reporting purposes or further evaluation.
Okay, perfect. Well, Curtis Dickinson of Olympus Corporation, looking at the OmniScan X3 phased array flaw detector, right?
Yes, sir.
With TFM.
Now with TFM.
Now with TFM. All right. Curtis, thanks for joining us today.
Thanks for having me.
And that is it for today's QDL. Thanks for joining us today. As usual, if there's a piece of equipment or a guest you'd like us to bring on the show, let us know. You can just send your request to qdl@qualitydigest.com, and I'll do my best to bring them up here. So thanks for joining us, and we'll see you at the next QDL. So long.